Okay, so what is a switching power amplifier? You might have seen, one question that should have appeared. I was expecting this question to come when I was talking about mixer and trying to introduce a power amplifier. That what happens if I simply say that what prevents us from doing this, right? So this was BCT. This is at FC and multiples of FC. Let's say we have filtering and all those things in place. If this is V in T, what prevents us from simply connecting to 50 ohm? So what I'm essentially saying that if this is V in T, frequency at FBB, what prevents us from directly connecting to 50 ohm? Which is ideal. Everything is ideal. Everything is ideal. You might say that, okay, V in T inherently probably doesn't have enough swing, right? So, I took the example of maybe it has a 10 millivolt of swing when I introduce this. But I can then say that I can put an amplifier here, right? I can put an amplifier here. That should also be fine to some extent. I can increase that swing. So let's say swing is not the problem. So I can have a swing. Kind of. But yeah, so ultimately it comes to that, but there's another main reason that I am trying to understand. So yeah, go ahead. That we'll anyway have. We'll need to use a filter. That we understand. Right? So here, what Dhruv is pointing out, here I am going to have tones of FC. When I say tones, multiples of FC plus minus FBB. So that we are going to have, that we have to filter. There is no way around it. We need that, right? But in terms of simply power delivery, is this fine? The way I have drawn it, it is fine. There is no trick here. But the issue is, this is not an accurate representation. So you must have heard people say my signal is weak or my signal is strong. What is meant by my signal is weak? What? Okay, I am not receiving the signal properly. That is in the context of a receiver. But in general, what do you understand if I say my signal is weak? What does it mean? Exactly. So what is meant by the strength of the signal? Power of what? Amplitude of what? Amplitude of voltage, current? Amplitude of the voltage, right? So I observe the signal in a spectrum analyzer and see a voltage. Now, spectrum analyzer has an inherent impedance, right? So if I change the impedance, the voltage can change, right? It can, in principle, right? So voltage is some current times R. If I change R, the voltage can increase, right? So again, coming back, what is meant by a strong signal? I got the answer, which is essentially the power content in the signal is high versus power content in the signal is low. But when I say power content, what does it mean? It's just a EM wave, right? Amplitude of what? Moment is a voltage, there is a, when I say power, which essentially means that there is I'm basically saying there is a resistance associated with it. The power, how much power I can deliver. That essentially is it, right? So when I say strength of the signal is low, which means I'm sensing the signal in some way. How am I sensing? I'm probably using some sort of resistor to heat it up, you can say. So what is the heating capacity of the signal, one might say. Right? So essentially V squared over R. Right? So there is an R associated with it. Now, the issue is you never have signals with pristine voltage sources, because the pristine voltage source can deliver infinite power. Right? So however small the amplitude is, if I have a voltage source like this can deliver infinite power. I can ask for infinite current, it is going to provide infinite current. This model. So this model is not accurate. Right? So how much power it can deliver is limited by, for a particular voltage that it can give, there is an associated Thevenin impedance, right? If the Thevenin impedance is high or low, that decides whether the signal is weak or strong, right? So essentially you have a resistance associated with it, which is an internal resistance, source resistance we call it. If the source resistance is high, you have the power, if the amount of power that you can extract will be limited, right? So, I mean, again, we know from maximum power transfer theorem and all, if I have to deliver for a particular source resistance, the load resistance can be RS, and that is the only condition for which I can find out how much power, that is the condition for maximum power transfer and so on, right? So again, when we say heuristically a signal is weak, we essentially imply that it comes, whatever is the source, comes in with a pretty high source resistance with respect to the load, right? With respect to the load and so on, right? So fine, but for the same source resistance, you can say that one signal has higher amplitude, one has low, one is high, which means the one is a stronger signal than the other. Unless you specify source resistance, it is very difficult to justify whether one signal is higher strength or than lower strength, right? So, but in wireless, it is often assumed that everything is 50 ohm. So when a moment we say it's a stronger signal, we assume that across 50 ohm load, one delivers higher power than the other. So that's the inherent assumption. So as it turns out, in these cases, if I use an amplifier also, to raise the signal, the example that I was trying to give earlier, typical amplifiers are again common source amplifiers and some variants of that. The output impedance are never 50 ohm. They are much higher than 50 ohm. Right? You have done projects in the previous semesters, right? So the load that typically the load that we design in analog circuit classes and amplifier drives is either capacitive load or some resistive, which is of kilo ohms, maybe 10 kilo ohms or 1 kilo ohm or something like that, right? So that is a typical range of loads that our amplifiers can drive efficiently without losing bias or having very poor efficiency, right? So that is one of the reasons this directly connecting the mixer in this way doesn't help, right? So that's why this wouldn't have this wouldn't have helped delivering significant amount of power. We needed a power amplifier separately. But what if we do this in this format, right? So let's say we have this mixer. So this mixer is there. So this is this is not a sinusoid per se, but a signal containing FC plus FBB, NFC plus minus FBB, right? This is a signal which contains this. And what happens if I simply say that I connect this signal to the switch of ideal switch, to the control voltage of the switch, right? So this signal is high frequency signal, right? This goes like something like this. Okay. And let's for the time being limit ourselves and say that this is only switching at FC, right? Let's keep things simple. Let's say it is only at switching at FC. And I say that this is connected to a supply, VDD. Now, VDD is an ideal voltage source. It has a resistance, but its resistance can be much less than 50 ohm. right? Can be 1 ohm, 2 ohm, maybe 10 ohm or something, right? So this is doable. This is not a big problem. So now can I drive a 50 ohm load? So to make matters simpler, what I will do is I will say that instead of the control voltage being a sinusoid, let's assume the control voltage is a square wave at FC. Right? So let's say I say that this control voltage is a square wave whose period is Tc, right? So then what are you going to see here? It's a square wave of value VDD to 0, right? So your VCT, or let me call it VLT, essentially be a square wave of value going from 0 to VDD. What is the strength of the fundamental of this? So this is again at FC, right? So this has tones, right? This will have tones. If I break it in Fourier series, so it will have a DC, then it will have FC. So again, the strength is 1 over pi, this is 1 over 2. Then at 2F you don't have anything. Then at 3FC you have 1 over 3 pi. The same thing that we did in the previous lecture, right? So if we did this, how much efficiency did we get? 40% or so, right? And that too when we had the DC. So if we could remove the DC part, right? So we would have gotten a higher efficiency, right? So as it turns out, this is also a power amplifier, right? This is also a power amplifier which can give you higher efficiency than your than the linear power amplifiers. But this requires an additional set of filters at the output. You cannot simply do this. You'll have to say that. So your this is VDD. So this comes from mixer. This is a square wave. So if you do this, you are going to radiate all other frequencies also. So you cannot do that. So which essentially means that you need a filter here at the output and then transmit it to 50 ohm to the antenna. 1 second. Yeah.
Where do we actually filter out the DC component?
Here I have not shown. Here I have shown only one switch, right? You can basically, the question that he has is where are we filtering out the DC component? What you can do essentially is break it up into multiple paths. In this case, I can break it up into 2 paths. And make it a differential antenna. I can put a balun or inductor, right? An inductor having some sort of mutual inductance. Assume a transformer, an ideal transformer. It takes plus, minus, and this goes at 0 degree. This goes at 180 degree out of phase. That is, when this swings high, the other one swings low, right? So you develop a differential voltage across the input of a transformer. This is a transformer. So at the output, the DC of the input is going to get cancelled because both sides have the same DC. And if you see 50, so the 50 ohm will not have any DC component, right? So that anyway filters it out. That's one of the ways, right? An example for it. So we'll deal with these things in detail when we come to the PA later on in the course. Okay, fine. So what is the moral of the story? The moral of the story is PAs are a major bottleneck in an RF transceiver. People have been trying to build different types of PAs for a long time to increase the efficiency. Efficiency of a linear PA is much poorer than that of a switching PA. You can make switching PAs in theory. Theoretically, you can make switching PAs with efficiency of 100% in theory, right? Because ultimately, if you think of, let's say, for example, if you think of an inverter, which is essentially a set of switches, and this is the control. The top one is PMOS, bottom one is NMOS. And let's say this swings. Then, and assume that S1 and S2 are non-overlapping. That is S1, when S1 is on, S2 is off, and so on. So then all the current from VDD either flows into the resistor or goes this way. And there is no direct path between VDD and ground, right? And you can use, if you can use some sort of smart filtering, you can basically see that all the current that you are driving, or you are extracting from the supply. Here you need obviously a capacitive coupling and so on. All the current that you are driving from taking from the supply is being used to drive the load. Nothing is used for biasing, because it's a switch. It's the inverter, right? There is, if I neglect the leakage current or the prober current, or through basically the VDD to the switching current, VDD to ground switching current, then there is no loss. So in principle, in theory, you can postulate that these type of power amplifiers, which are essentially inverter based, can give you 100% efficiency. We can prove, but obviously there are losses, and that doesn't really help. Okay. Any questions so far? So till now we have, on a very broad level, we have had an overview of how to sense a signal, how to convert it to a different frequency, the reasons behind it, and how to filter it. We haven't talked about filter, but the necessity of filtering. And then we figured how to transmit. Why to transmit? What are the issues related to transmission? And why it is important that some block need to be always on and some block needs to be always sometimes turned on and off and so on, right? So on a very broad scale, this is what we have till now. We have the transmitter chain, so as to say. So we have a DC, or we have an input signal, which is VINT or VBBT, where BB is the baseband signal. Baseband is often referred to in RF lingo as the low frequency input. And when I say FC, C is referred to the carrier frequency, because ultimately it is assumed that high frequency signal is carrying the low frequency signal on its back, because, right? So ultimately you had to modulate the low frequency signal to a high frequency to ensure it travels through the antenna of a reasonable size. So we saw that we had a mixer ideally operating at a single tone, but difficult to make, so generates multiple tones. Then we had a filter, then we had a PA. And this goes out. So once it transmits, it's this is assume that this is your cell phone that is transmitting. Your cell phone also has a receiver, because you don't only want to speak, you want to listen also. So which essentially means that there is probably another antenna on the receiver side. right? But what is the difference of, so now this is, by the way, a transmitter chain, very basic model of a transmitter chain. But if I focus on the receiver side, so you have to do exactly the opposite, right? You have to sense it, and then this is at FC plus minus FBB. You have to sense it and then mix it down to the baseband voltage and then do some processing, right? Because the only reason we were at high frequency is because we wanted to send it out. Inside the chip, processing is not necessarily needed at FC, right? And in fact, I would like to have processing at as low frequency as possible inside the chip because it saves power, right? So the first thing then to say is that how do I receive it, right? Now the issue with this is if I okay, so the difference between, one of the fundamental difference between whatever the signal that is getting transmitted in this case, which is of the order of 10 milliwatt, the issue is the amount of power that you are receiving here is coming from somewhere else. The base station is somewhere else, maybe 1 kilometer from wherever you are sitting, which means that the power that you are going to receive on the antenna of your cell phone is much, much smaller than this 10 milliwatt, right? Why was this 10 milliwatt necessary? Because you wanted to ensure that your signal reaches an antenna which is somewhere far, maybe 1 kilometer away. And if you assume that there is certain amount of loss from the cell phone transmitted to that antenna, the equivalent amount of loss will be there from that base station when the signal comes back to your cell phone. And typically these losses are humongous, so much so that you cannot express in linear scale. So this number that you typically what you can receive is of the order of this is less than 1 nanowatt, picowatt or so, right? That is the, I mean, I would say of the order of few picowatts, tens of picowatt. So that is the strength of the signal that you receive. Now, as you can see, going from milli to pico and nano is a mess. So what is it that we normally, which type of maths do we normally do when you have to refer to signals of different or numbers of different magnitude? Let's say at the same time, I want to do maths having 1 nanowatt or 10 power minus 9. On the other hand, I also want to process 10 power minus 3 or 10 power minus 1 log scale, right? So dB essentially. So that's why in RF lingo, almost always dB is the unit of choice, right? Or you always go with dB. So 10, when I said dB, now dB is essentially a ratio, right? Just saying a dB doesn't mean anything unless I say that what am I comparing with. I can always take a number and do a dB of it, right? 10 log something is a dB, but what is that dB? When you say 10 log some number, you assume that the denominator is 1, right? When you say dB dB essentially means 10 log 10 of to the base 10 of something, in this case power, which is divided by 1. If I just say dB, it means this. But so that is why you never should say dB. When we say this, we essentially mean it is dB watt. It is assumed that this is 1 watt. Okay. If you don't say anything, if you simply take dB, this is what it is assumed. The more common nomenclature that is used in RF is dBm, which is 10 log P expressed in milliwatt divided by 1 milliwatt. This is power expressed in watt. Okay. So for example, 10 milliwatt power. So if P equal to 10 milliwatt, this is equivalent to, in dBm, 10 log 10 milli by 1 milli, which is 10 dBm. Right? So if a PA is transmitting 10 dBm, 10 milliwatt power, which essentially means it's transmitting 10 dBm, very handy number. Often you will say that, you will see people refer to as a 0 dBm PA, right? So similarly, a 0 dBm will refer to how much? 1 milliwatt, right? So every power corresponds to 10 addition of 10 in dB, right? Give me 2 minutes, we'll stop here after that. And if you are very familiar with dB, no issues, but if you are not so, there are some pitfalls. Be mindful of that. Let's say I am adding two quantities in dB, right? For example, I say that P1 is 10 dBm and P2 is 1 dBm, right? So if I say what is P1 plus P2 expressed in dBm, approximately this is what? This is approximately 10 dBm, right? Why? Because this is 10 milliwatt. This is approximately how much? 1 dB, 0.1? You sure? 0 dBm is 1 milliwatt. It has to be at least more than 1 milliwatt. So approximately it comes down to 1.1 milliwatt, right? So yeah, right? So when you add up two numbers in power, they don't directly add up. So you have to be slightly careful of that. So typically it's always the larger selection, right? So if I add 100 dBm plus 50 dBm, it basically becomes 100 dBm. So that you have to be slightly careful about. So